What if I told you that empty space isn't empty at all? That it's actually buzzing with a kind of hidden, invisible energy? Well, today we're diving deep into that very idea, and our guide is a truly groundbreaking paper from 1975 by the physicist Bryce DeWitt. We're going to take a journey from a simple experiment you could do in a lab all the way to the chaotic edge of a black hole, all to uncover the secrets of the vacuum.
DeWitt starts his paper with this quote, which is pretty intense, right? But he wasn't talking about some substance or a bad habit. No, he was talking about an idea he felt physicists had been addicted to for decades.
So what was this addiction? It was the comfortable, simple belief that space-time is just a smooth, flat, empty stage where the universe happens. But relying on that simple picture came at a cost. It was actually blinding physicists to some of the most profound and frankly weird secrets the universe has to offer. So today we're going to explore the penalty. We're going to see what they were missing.
So here's our plan. We'll start with this addicting idea. Then we'll look at the strange energy of nothing. From there, we'll see how you can actually create particles just by moving things. Then we'll take it to the extreme, spinning black holes, and then find out how black holes can actually glow. And finally, we'll see how this all leads to a huge, unfinished picture in physics.
You know, the first clue that our whole empty vacuum idea was wrong didn't come from some massive telescope staring into deep space. Nope. It came from a surprisingly simple experiment right here on Earth.
So, picture this. You take two perfectly neutral metal plates, and you place them parallel to each other in a perfect vacuum. Now, old-school physics would tell you absolutely nothing should happen, right? But in the real world, something very strange does happen. The plates actually get pushed together by some mysterious force, and it's a force we can measure.
This is known as the Casimir effect, and it's our first big clue that the vacuum is anything but empty. It's actually this roiling sea of what we call virtual particles, constantly popping into and out of existence in pairs. The two plates act like walls, and they change which of these virtual particles can pop into existence between them. This creates an energy imbalance between the inside and the outside, and that imbalance generates a real physical push.
DeWitt calls this pure vacuum energy. I mean, think about that. There are no real, tangible particles pushing the plates, and yet the effect is real. This is proof that empty space itself has energy. But here's where it gets even crazier. DeWitt points out that this energy density is actually negative, which is something classical physics would tell you is totally impossible.
Okay, so this leads to a really cool question. If just putting two static plates in a vacuum can reveal this hidden energy, what happens if we start moving them? What happens if we shake things up?
Well, the result is nothing short of astonishing. DeWitt explains that if you accelerate a neutral object, like a mirror, just moving it back and forth really fast, you are essentially shaking the vacuum itself. And by doing that, you can pump enough energy into these virtual particles to promote them into real, detectable particles. You can literally create matter and light out of what we thought was nothing just by moving something.
All right, now let's take that idea and just crank it up to 11. We're going to go from a little moving mirror in a lab to the most extreme accelerators in the entire universe, a spinning black hole.
Around a spinning black hole, there's this really bizarre region called the ergosphere. In this area, the black hole's rotation is so powerful that it literally grabs the fabric of space-time and drags it along for the ride. As DeWitt puts it, nothing, and I mean nothing, inside the ergosphere can stay still. You are forced to spin with the black hole.
And this is where things get even weirder. It turns out a particle can fly into this ergosphere and then get shot back out with more energy than it went in with. It's a process called superradiance, and it effectively steals a tiny bit of the black hole's rotational energy. So instead of just being a cosmic vacuum cleaner, a spinning black hole can actually become a source of power.
All of these pieces, the energy of the vacuum, creating particles from motion, the weirdness of spinning space-time, they all come together to paint a new picture of black holes, thanks to a discovery that truly changed everything. Right at the event horizon, the point of no return, the black hole's gravity is so intense it can do something incredible. When a pair of virtual particles pops into existence, the gravity can rip them apart. One partner gets sucked into the black hole, carrying negative energy with it, while the other one escapes out into space. And because its partner is gone, it can't just disappear. It becomes a real particle. So to someone watching from far away, it looks like the black hole is spitting out radiation.
Now, this isn't just random static. DeWitt emphasizes that this radiation has a perfect Planckian spectrum.
That's a technical term, but what it means is that the black hole glows with a pure thermal heat, just like a hot piece of metal glowing in a forge. It means the black hole has a temperature.
And the physics behind this is just beautifully, elegantly simple. The temperature of a black hole only depends on one thing, its mass, m. And here's the really counterintuitive part. The more massive a black hole is, the colder it is. The tiny ones are the ones that are searingly hot.
DeWitt calls this whole thing Hawking's astonishing discovery. And it is, because it means black holes aren't really black, and they aren't permanent fixtures of the universe. They have a temperature, they radiate away their energy, and over truly unimaginable timescales they will shrink and eventually evaporate completely.
So we've come a long way. We've seen that empty space isn't empty, that black holes can glow and even disappear. But this incredible new understanding also brings with it a really deep, really difficult problem, one that physicists are still fighting with to this day. So let's just quickly recap what we figured out on this journey. The vacuum is not empty, it's full of energy. Motion can literally create matter out of nothing, spinning black holes can be energy sources, and all black holes have a temperature, they glow, and eventually they evaporate.
With all of these incredible new insights, what's the catch? What's the huge challenge that people like DeWitt were suddenly facing?
Here's the problem. When physicists actually sit down and try to calculate the energy of the vacuum in curved spacetime, around a black hole, for example, the math completely breaks. The equations just spit out the answer, infinity. And whenever you get infinity as an answer in physics, it's a giant red flag. It's the universe telling you that your theory is missing a crucial piece of the puzzle.
And this brings us right to the edge of one of the biggest unsolved mysteries in all of science. If a black hole can swallow a star, or a planet, or a book, and then it slowly evaporates away into simple thermal radiation, what happens to the information about what it ate? Does it just vanish from the universe forever? That would violate some of our most fundamental laws of physics. Or does it get out somehow? This is the famous black hole information paradox, and it's a mystery that all started with the simple, world-changing realization that empty space isn't.